There is a specific kind of quiet that descends on the Storm Prediction Center in Norman, Oklahoma in the days before something genuinely rare is about to happen. Not dramatic. Not the kind of quiet that gets noticed from the outside. The kind that comes from a room full of people who have spent their careers learning to read the atmosphere the way other people read faces, and who are now looking at something that doesn't come along more than a handful of times in any given decade and trying to find the right language for it. Language matters, because the language is what gets transmitted to emergency managers, to local National Weather Service offices, to broadcast meteorologists, to millions of people in the path of something that the historical record can contextualize but cannot fully prepare you for. And in mid-April of 2026, the people in that room were looking at something that required very careful language indeed, not because they were uncertain, because they were certain, and what they were certain of was genuinely extraordinary. A sustained, multi-day, multi-system severe weather outbreak, unlike anything the central United States had experienced since years that meteorologists still reference by date rather than by description. And it was not coming, it had already started. And the part that was still coming was shaping up to be worse than what had already happened. That is not a sentence that gets written casually. That is a sentence with specific, measurable atmospheric support. And understanding what that support looks like, what the physics behind it actually means for the people standing in its path, is the only honest way to explain why this outbreak earns the word rare in a profession that is professionally resistant to dramatizing the weather. Part 1. The week that wouldn't quit. You need to understand the full sequence of what happened across the central United States in the week of April 13th through April 18th, 2026, because taken as a whole, it represents something that the historical record of severe weather in this country places in a specific and rarefied category. Not the worst outbreak ever, not the deadliest, not the most tornadoes in a single day. Something in some ways more unsettling. A sustained, continuous, reloading, severe weather pattern that refused to exhaust itself, refused to produce a meaningful gap, and kept presenting new, organized threats to the same general corridor of the country day after day after day for the better part of a week. Monday, April 13th. The opening act. A supercell complex fires in eastern Kansas in the evening hours after the atmospheric cap. A layer of warmer air aloft that acts as a lid on convective development weakens enough to allow the instability beneath it to release. The Storm Prediction Center receives at least 14 preliminary tornado reports between 2317 UTC on the 13th and 0130 UTC on the 14th, spanning Kansas, Minnesota, Iowa, and Wisconsin. 2 hours and 13 minutes. 4 states, 14 tornado reports. An EF2 strikes southern Ottawa, Kansas, injuring 3 people, damaging a house east of the city. Another EF2 from the same supercell tracks through Miami County, impacting roughly 100 structures and significantly damaging 50 of them. An EF1 south of Mound City and Pleasanton destroys a mobile home, injuring 2 people. Tennis ball hail falls across parts of southern Minnesota. Tuesday, April 14th. The Storm Prediction Center places eastern Iowa, northern Illinois, and southern Wisconsin under an enhanced risk, level 3 of 5. MLCAPE values of 2,500 to 3,000 joules per kilogram. Deep layer wind shear around 50 knots. A warm frontal boundary draped across the upper Midwest, acting as a focus for discrete supercell development. A particularly dangerous situation tornado warning, the rarest and most serious escalation in the National Weather Service warning vocabulary, is issued for the area near Union Center, Wisconsin. Significant damage to homes, roads made impassable. Millions of people from Milwaukee to Detroit and Ann Arbor inside tornado warnings from Tuesday night into early Wednesday. A tornado emergency issued near the Illinois-Indiana border as a cyclic supercell tracks more than 150 miles through the risk area. Baseball-sized hail and larger. Nearly 100 hail reports in the first 2 days alone. The SPC internally discussed whether to upgrade the Tuesday outlook to a moderate risk, level 4, but held back because confidence in convection remaining discrete long enough to sustain supercell mode was not high enough. That is not reassurance. That is the SPC telling you they considered upgrading to one of the rarest designations in their toolkit, and only didn't because one specific variable remained uncertain. Wednesday, April 15th. Another round. Damaging winds and large hail from Texas through Chicago. Tornado risk remains highest in Iowa, northern Texas, Oklahoma, and southeast Kansas. Flooding begins to emerge as a compounding threat as repeated heavy rainfall loads soils and raises river levels across the Great Lakes corridor. Northern Michigan receives so much rain in such a compressed period that Pellston Regional Airport floods both runways and closes through at least Friday. The Weather Prediction Center warns explicitly of repeated rounds of severe thunderstorms and heavy rain through at least April 16th. Multiple low-pressure waves tracking along a frontal boundary. Daily storm redevelopment. No break. Then Thursday is relatively quiet. The thinnest possible gap in a week that has been delivering organized severe weather every day since Monday. And then Friday, April 17th. And this is where the word rare stops being a descriptive adjective and becomes the only honest term available. Part 2. The thing about Friday that the models kept agreeing on. There is a concept in severe weather forecasting called signal-to-noise ratio, and it describes the relationship between the atmospheric data that genuinely predicts a significant event and the background variability that can mimic the appearance of a signal without representing real threat. High signal-to-noise ratio means the models are pointing in the same direction, the physical ingredients are clearly present and clearly organized, and forecaster confidence is high. Low signal-to-noise ratio means uncertainty dominates, the models disagree, and the honest forecast is essentially a range of possibilities with no strong central tendency. By Tuesday, April 14th, the signal-to-noise ratio for Friday's event was already high, and it kept getting higher, not because the models were exaggerating, because the physical setup that was being forecast was real and measurable and unambiguous. A strong upper-level trough oriented from Montana to the southwest was going to eject eastward into the plains on Friday and Friday night. That trajectory, that timing, that specific ejection dynamic was appearing in every major forecast model with consistency that meteorologists describe in terms of ensemble agreement. The percentage of independent model runs pointing toward the same outcome. By midweek, the ensemble agreement for the Friday severe weather setup was the kind of number that makes experienced forecasters uncomfortable with the word forecast, because at that level of agreement, it starts feeling more like a certainty than a probability. The atmospheric environment ahead of this trough was being described in the SPC's own technical language with terms that deserve to be read carefully. ML-Kp of 2,500 to 3,500 joules per kilogram across the warm sector. That range, 2,500 to 3,500, is the range that supports what forecasters call robust convective development. It is not the marginal instability that produces ordinary thunderstorms. It is the kind of fuel loading that, when combined with the right wind profiles, generates storms capable of long tracks, violent rotation, and tornado production that extends well beyond what most people imagine when they picture a tornado. Forecast soundings, the virtual atmospheric profiles that model the vertical structure of the environment at specific locations, were showing large, curved hotographs that became elongated above 2 to 3 kilometers. A hotograph, in the simplest possible terms, is a diagram that represents how the wind changes direction and speed as you go upward through the atmosphere. A large, curved hotograph with elongation at certain levels is the signature of an environment that is not just favorable for rotation. It is optimized for it. It represents the kind of wind shear profile that produces supercells capable of keeping their rotation organized over long distances, capable of generating tornadoes that stay on the ground for tens of miles rather than a few seconds, capable of producing the kind of extended track that earns EF ratings that are measured in hundreds of meters of width and miles of path length. The SPC's technical discussion for Friday identified a specific corridor where the tornado environment was expected to be most favorable, northeast Iowa into central Wisconsin. The language was precise. Low-level storm relative helicity maximized, mixing ratios near 14 grams per kilogram. Very steep mid-level lapse rates. Forecast soundings indicated large curved hotographs. This area, the SPC wrote, may become a focused corridor for stronger tornadoes. Not tornadoes in general, stronger tornadoes, in a specifically identified geographic corridor, with the atmospheric physics explicitly supporting that assessment. Part 3. 2 machines running at the same time. What made Friday's setup structurally different from anything earlier in the week was not just the risk level, it was the architecture. Because Friday was not one severe weather regime, it was 2 operating simultaneously, in different parts of the same general threat corridor, each with its own trigger mechanism, its own storm mode preference, and its own hazard profile. And understanding both is the difference between treating Friday as a bad thunderstorm day and understanding what the people in the path of it were actually facing. The first regime was the crashing cold front. A deep trough ejecting eastward from the Rockies generates a surface cold front that accelerates southward and eastward as the upper-level dynamics strengthen. This front was forecast to be moving into the upper Midwest during the afternoon hours of April 17th, sweeping through Iowa, Nebraska, and Missouri in a configuration that would bring it into direct contact with an air mass that had been building for days. Surface dew points in the mid to upper 60s Fahrenheit ahead of the front. Temperatures in the 80s. The warm sector, the region of warm, humid, unstable air between the cold front and the dry line, was loaded to a degree that the models consistently described in terms of the highest CAPE values of the entire week's outbreak sequence. This front, moving into that air mass, was capable of producing supercells along its leading edge. It was also capable of generating what meteorologists call a QLCS, a quasi-linear convective system, as the discrete supercells eventually consolidated into a squall line. And a QLCS in a high-shear environment carries its own specific and underappreciated tornado threat. QLCS tornadoes don't look like the classic plains supercell tornado on a weather radar scope. They appear as brief, intense circulations embedded in a line of storms, rotating within mesovortices that form along the leading edge of the squall line. They are short-lived, often less than a few minutes on the ground. They give very little warning. And they are the reason tornado warnings sometimes appear to pop up directly ahead of a squall line and then expire within minutes, because the circulation that triggered the warning was real. It was there, and it was gone almost before the warning could reach the people in its path. That is the northern regime. The second regime was the dry line, the boundary between the moist Gulf air flowing northward from the south and the dry continental air pushing in from the west, stretching across Kansas, Oklahoma, and into North Texas. A dry line on a high cape April afternoon is the trigger mechanism that has produced more significant tornado outbreaks in the historical record of the central United States than any other atmospheric feature. It is where the warm, moist, unstable air on the east side of the boundary meets the dry air that allows visual clarity and storm isolation on the west side, creating the conditions that allow discrete supercells to organize and maintain their structure for hours rather than minutes. The dryline regime on Friday was carrying ML Cape values that, in some areas of the forecast soundings, were approaching 3,500 joules per kilogram. Wind shear strong enough to support not just supercell organization, but the specific type of supercell with mesocyclone depths and rotation intensities that the SPC's own guidance associates with the potential for long-track violent tornadoes. The critical uncertainty, the thing forecasters were watching most carefully as Thursday transitioned into Friday, was the timing of the cold front's arrival relative to the dry line. If the front moved at an expected pace, the dry line would have time to mature in the afternoon heat. Storms would organize along it before the front arrived and disrupted the boundary, and the two regimes would operate in parallel for several hours. If the front accelerated and overtook the dry line earlier, the dry line's storm production would be suppressed, and the frontal regime would dominate. Either way, severe weather was certain. The only question was whether both machines ran simultaneously or whether one overtook the other. Part 4. What 100 tornadoes in a week actually means. By the time the full April 2026 outbreak week was over, storm survey teams would be counting tornadoes the way accountants count losses after a flood. Not with urgency, because the urgency had passed, but with methodical care, because getting the number right matters for insurance, for history, for the communities that need the documentation to access federal aid. More than 100 tornadoes confirmed across the full week of activity. Multiple EF2 ratings, multiple particularly dangerous situation warnings. Baseball-sized hail documented in the Kansas City metropolitan area, an EF2 tornado emergency issued for Knox, Indiana, where a cyclic supercell continued producing tornadoes well after it had already damaged a broad swath of communities, a large EF1 near Wheatfield, Indiana, causing 3 injuries from the same system, the Ann Arbor area of Michigan receiving tornado warnings and storm damage in the overnight hours as the system moved east, power outages measured across multiple states simultaneously. The ground saturated to the point that the Weather Prediction Center was explicitly flagging compounding flood risk, not from a single heavy rainfall event, but from the cumulative input of repeated rounds of heavy convective precipitation on soils that had been receiving significant rainfall for days. To understand why 100-plus tornadoes in a week is genuinely unusual requires knowing what normal looks like. The long-term historical average for tornado activity in the entire month of April across the United States is approximately 182 tornadoes for the full month. The April 2026 outbreak produced the majority of that monthly average in a single compressed week. And it did so not through one giant outbreak day, not through a single high-risk event like the ones that define the worst outbreak years in the historical record, but through sustained day-after-day production that reflects something specific and rarely achieved about the atmospheric pattern that was in place. The pattern had locked in. The jet stream was configured in a way that kept feeding energy into the central United States along a corridor that ran roughly from the southern plains to the upper Midwest. Each wave of energy rotating along the jet stream arrived with enough moisture feed from the Gulf, enough instability, and enough wind shear to reload the severe weather environment before the previous event had fully dissipated. That reloading mechanism is what separates a single outbreak day from a multi-day outbreak sequence. And multi-day sequences with this kind of sustained production and this kind of geographic consistency across a full week are the events that weather historians reference by year rather than by date. Not April 14th, 2026. April 2026. The distinction is meaningful. It means the event was larger than any individual day within it. Part 5. The rarity problem and what it does to people. Here's the part of this story that is more difficult to quantify than KP values and wind shear and hodograph geometry, but that is arguably more consequential for understanding what this outbreak actually produced on the ground. The rarity of what was happening worked against the people in its path in a specific and cruel way. By midweek, after 3 consecutive days of tornado watches and severe thunderstorm warnings and emergency alerts and shelter-in-place notifications, a significant portion of the population in the affected corridor had reached what psychologists and emergency managers call alert fatigue. The 47th tornado warning in 4 days does not produce the same behavioral response as the first. The 3rd consecutive day of enhanced risk outlooks does not generate the same urgency as the first enhanced risk of the season. The emergency alert system is effective. The NWS warning system is effective. The SPC's risk categorizations are effective. They are built around the assumption that the people receiving them have a baseline level of alertness that has not been depleted by 5 consecutive days of the same system asking them to pay attention. When the system overrides your sleep with an emergency alert at 2 in the morning for the 4th time in a week, the cognitive calculation changes, not because the threat isn't real, because the human brain was not designed to sustain maximum alertness indefinitely. It was designed to return to baseline after a threat passes so that it can respond fully to the next one. An outbreak that never allows the baseline to reset is, in a specific psychological sense, more dangerous than a single massive event because it gradually degrades the very resource, human attentiveness, that the warning system depends on to save lives. Emergency managers in the affected states were acutely aware of this dynamic by Thursday and Friday of the outbreak week. The challenge they were navigating was how to communicate that Friday's threat, despite arriving at the end of a week of continuous severe weather activity, despite the obvious alert fatigue, despite the understandable exhaustion of communities that had spent 5 days in an elevated risk posture, was genuinely elevated above what had come before it. Not routine, not another round of the same thing, something that the atmospheric setup specifically and the SPC's own language about stronger tornadoes in a focused corridor specifically required a fresh level of attention. That is not a problem that better radar technology solves. It is not a problem that a more accurate forecast model solves. It is a problem that lives at the intersection of atmospheric science and human psychology, and the solutions to it are not primarily meteorological. They are community level. They involve the relationships between people, between neighbors, between employers and employees, between parents and children, that determine whether a tornado warning at 10 p.m. on the 5th day of an outbreak week reaches a person who is already asleep, already tired, already half convinced that this one will probably miss them too. The warning system worked as designed. The science was accurate and timely. And still, the fundamental tension at the center of every severe weather outbreak remained unresolved. Between what the atmosphere is capable of and what the warning system can do about it, between perfect forecasting and imperfect human behavior, between all the information a person needs to make the right decision and the gap between having the information and acting on it in the specific, exhausted, alert-fatigued middle of a week that had been asking people to pay maximum attention since Monday. The outbreak was rare. The science behind it was understood. The warning lead time was real. What happened in the space between the warning and the shelter is the part that no atmospheric model can simulate, no radar system can close, and no risk communication campaign has fully solved. That space is where people live, and it is the only thing ultimately that this week, or any week like it is actually about.